In this lecture, we will talk about solutions, electrolytes, dialysis, and osmosis. So solutions are mixtures, homogeneous mixtures of more than two substances or two substances. Solution is formed when the molecules or particles of the solute and particles of the solvent attract sufficiently, thus reducing the overall energy of the mixture. Generally, the solution has two components: the solvent, which is present in much larger amount, and the solute or the solutes that are present in much smaller amounts. For instance, in a solution of salt, water will be identified as a solvent, while salt will be the solute. Solutes, as well as solvents, can be liquids, gases, or solids. The principal idea behind the solutes is that they are distributed evenly throughout the solution. When solutes and solvents mix, they have same physical state, and solvents and solutes cannot be separated by filtration. So basically, a true solution is the one that can only be separated by, for example, evaporation, but not filtration. Solutes within the solution cannot be seen with the naked eye, but they can give solution a color. So for instance, if you mix a solute, which is copper to sulfate, with water, eventually it will dissolve in water, and during the dissolution, particles copper sulfate will become evenly dispersed among the molecules of solvent, which is water in this case. There are different types of solutions. For instance, air is an example of a solution where gas is dissolved in gas. The primary solute is oxygen and the solvent is nitrogen. Liquid solutions, you'll know them: soda water and household ammonia represent solutions of carbon dioxide and ammonia in water respectively. Liquid in liquid is the kitchen vinegar, acetic acid dissolved in water. Seawater and iodine tincture represent the solid and liquid solution: sodium chloride dissolved in water and iodine dissolved in ethanol respectively. There are even solid solutions like brass and steel. In brass, solid zinc is dissolved in solvent, which is copper, and in steel, carbon, which is solid, is dissolved in iron, which is solid as well. The most common solvents in nature is water. There's a polar molecule because oxygen and hydrogen, oxygen-hydrogen bonds in water are polar, and the molecule represents dipole. You can see it here in the picture with the partial positive charges on hydrogen and partial negative charges on oxygen. Partially negative charges on oxygen and partially positive charges on hydrogen form hydrogen bonds, which are critical for the proper structure of a variety of biological molecules. So basically the idea behind the formation of solution is this: molecules of solute and molecules of solvent interact within each other. When it's energetically preferred to form interactions between the solute and solvent rather than remain in the previous independent states, the solution is going to be formed. So here you can see three different situations when solutions are not formed because molecules of, say, some polar and non-polar chemicals cannot mix with each other. And this brings us to the conversation about like dissolves like. So polar solute and solvent will readily form a solution. Nonpolar solute and solvent will also readily form a solution. However, polar solute, such as sodium chloride, will not dissolve in the nonpolar solvent like cyclohexane. And on the other hand, nonpolar solute, let's say wax, is not going to dissolve in a polar solvent such as water. So what happens when polar solute gets dissolved in a polar solvent? Sodium chloride, as it dissolves in water, interacts with molecules of water. So you see it separates into positively charged sodium and negatively charged chloride ions, and each ion gets hydrated. Here you can see chloride ion hydrated by water molecules, and sodium ion gets hydrated by water molecules as well. Now, polar molecular compounds, compounds that do not separate into individual ions, interact with water by forming hydrogen bonds. For instance, polar organic molecule methanol is soluble in water because the polar OH group of methanol can form hydrogen bonds with the molecules of water. You can see it here. Methanol can form hydrogen bonds with the water molecules. Now, solutions are inextricably associated with the concept of electrolytes. Electrolytes are crucially important for proper functioning of the human body. Electrolytes such as sodium, potassium, chloride, and bicarbonate that are present in the blood and extracellular fluid. So strong electrolytes are compounds, usually ionic compounds, that when dissolved in water, completely dissociate, producing positive and negative ions. Solutions of strong electrolytes conduct an electric current. You can see the example here that the solution of a strong electrolyte has sufficient enough ability to conduct electrical current, sufficient conductivity to maintain the light bulb on. An example of a strong electrolyte is a sodium chloride. Now, not all electrolytes are strong. There are some weak electrolytes which dissociate in water just partially, forming a solution with just a few ions and mostly electrolyte existing in the form of molecule. So weak electrolyte, the solution of a weak electrolyte will still conduct electricity, but you can see that conductivity is much smaller and the light bulb is much less brighter. Non-electrolytes, such as sucrose, exist in water solution in the form of molecules. Since they don't produce ions in water, solutions of non-electrolytes cannot conduct an electrical current. So you can see here that the solution of sucrose essentially works as the dielectric, essentially works as an isolator without not conducting electricity. So this is the general overview and examples of strong, weak electrolytes and non-electrolytes. And that brings us to a really important conversation, important from the physiological and medical standpoint, conversation about the measurement of equivalent. So what is an equivalent? An equivalent is the amount in moles, well, it kind of corresponds to moles, the electrolyte or ion that delivers 1 mole of electrical charge. So solutions are always neutral. So the number of equivalents of the positive ion is always balanced by the number of equivalents of the negative ion. So in the fluids, often the concentrations of electrolytes are expressed in milliequivalents per liter, where 1 milliequivalent is the same as 1,000th part of an equivalent. So here's an example of the idea behind the equivalent. So if a solution contains 25 milliequivalents per liter of sodium and 4 milliequivalents per liter of potassium, the total positive charge is 25 plus 4, 29 milliequivalents per liter. In this case, the amount of chloride ions needed to balance 29 milliequivalents per liter should be the same, 29 milliequivalents per liter. Now, we mentioned before that one equivalent delivers 1 mole of electrical charge. Therefore, 1 mole of sodium will be the same as 1 equivalent of sodium. But 1 mole of calcium, since calcium has 2 positive charges, is the same as 2 equivalents of calcium. 1 mole of iron is 3 equivalents of iron, and so on and so forth. Let's calculate the equivalents in the patient's blood. So, patient has blood calcium level of 8.8 milliequivalents per liter. So, first question is how many moles of calcium ion are in 0.5 liters of blood in this example. So first let's find out how many equivalents of calcium we have per half liter of blood. So if measurement tells us that patient has 8.8 milliequivalents per liter, we multiply half a liter per this conversion factor and then multiply the product by this conversion factor where one equivalent is the same as 1000 milliequivalents. Crossing out milliequivalents in liters, we end up with 0.0044 equivalents of calcium. Now, we know that for calcium, 1 mole corresponds to 2 equivalents, which means 0.0044 equivalents of calcium can be multiplied by this conversion factor. 1 mole of calcium divided by 2 equivalents of calcium. So the final answer is 0.0022 moles of calcium in 0.5 liters of patient's blood. Now, what if chloride ion is the only ion that is present? What should be its concentration in milliequivalents per liter? Since the concentration of calcium is 8.8 milliequivalents per liter, then we need the same amount of negatively charged chloride ion to balance calcium, so it will be 8.8 milliequivalents per liter as well. In order to properly understand how the solutions are formed, we need to discuss the concept of solubility. For example, when concentration of uric acid in plasma exceeds a certain level, 7 milligrams per 100 ml, which is a solubility of uric acid, so uric acid starts to deposit at the joints, causing what's called a gout. So solubility is the maximum amount of a solution that can dissolve in a specific amount of solvent. For solutes, solubility is usually temperature sensitive, and it is usually expressed as the grams of solute in 100 grams of solvent, usually water, like this. So solutions of various compounds can be saturated and unsaturated. Unsaturated solutions contain the amount of solute that is less than its solubility, less than the maximum amount of solute that can be dissolved in that particular volume of solvent. Therefore, unsaturated solutions can dissolve more solute. Saturated solutions already contain the maximum amount of solute that possibly can be dissolved in that particular volume of solvent. At the bottom of the container, you can find undissolved solute, and essentially the solute and at the bottom and solute in the saturated solution, they are in the equilibrium. which can be expressed using this equation. So solute and solvent are in equilibrium, forming saturated solution. So solute constantly dissolves and recrystallizes. Solubility of solids, of salts, usually increases as the temperature increases. For all gases, their solubility decreases as temperature goes up. So paradoxically, cold water can dissolve more carbon dioxide than the hot one. Now, solubility of gases changes with the pressure. This change is described by Henry's law, which states that solubility of gas in a liquid is directly proportional to the pressure of that gas above the liquid, which means that at the higher pressure, more gas molecules dissolve in the liquid. When you have soda can, carbon dioxide in the soda is under high pressure. When you open that can, pressure suddenly gets released and molecules of CO2 start to get out of the liquid, and carbon dioxide essentially bubbles out of the solution. We need to mention that not all ionic compounds or salts are soluble in water. For sodium, potassium, and lithium, all their salts are soluble. All salts of ammonia are soluble. All nitrates and acetates are soluble. For salts of hydrochloric, hydrobromic, and hydroiodic acids, these salts that are formed with silver, lead, and monovalent mercury are insoluble. Among the sulfates, barium, lead, calcium, strontium are insoluble. Salts of carbonates, sulfides, hydroxides of these compounds are insoluble as well. So here are some examples. For instance, potassium sulfide is soluble. Calcium nitrate is soluble. Sodium hydroxide is soluble, but lead 2 chloride is insoluble. Aluminum phosphate is also insoluble. So next we need to discuss how to express the concentration of a solution. So concentration, here you take 5 grams of potassium iodide and then form exactly certain volume of the solution. Okay, so the concentration will be expressed as, for example, mass of potassium iodide over the final volume of the solution. So generally speaking, the concentration is expressed as amount of solute divided by the amount of the solution. Concentration can be mass percent, volume percent, mass volume percent, and molarity. So what is the mass percent concentration? So concentration of mass of a solute divided by the mass of the solution, which is composed essentially of the mass of the solute and mass of the solvent. So it is expressed in percent. So for instance, if you take 5 grams of potassium iodide and dissolve it in 95 grams of water, the total mass is 100 grams, and the concentration of potassium in that solution will be 5 over 100 multiplied by 100% will be 5%. So here, mass percent concentration of this solution, 8 grams over 50 grams of the solution, the mass percent concentration is 16%. So you need the grams of solute and the grams of solution. Okay, so this is just illustrates how we calculated it. Volume percent. You divide the volume of solute, liquid, by the volume of the solution. So this is the conversion factor for volume percent. Milliliters of solute over 100 mils of the solution. The mass volume percent is the mass of solute divided by the volume of the solution multiplied by 100%. So this is your final conversion factor. Molarity is the concentration expressed as moles of the solute in 1 liter of the solution. So 1 molar solution of sodium chloride is defined as 1 mole of sodium chloride in 1 liter of the solution. Now let's calculate the molarity of 0.5 liter of the solution of sodium hydroxide if this solution contains 6 grams of sodium hydroxide. So first we need to calculate how many moles of sodium hydroxide in 6 grams. To do this, we write a conversion factor which states that 1 mole of sodium hydroxide is equivalent to 40 grams of it. Then we multiply it by 6 grams and we get the result that 6 grams of sodium hydroxide are equivalent to 0.150 moles of sodium hydroxide. Then write the concentration expression. Molarity is equivalent to moles of the solute divided by liter of the solution. So 0.150 moles of sodium hydroxide divided by 0.500 liters of the solution, which gives us the answer 0.300 moles of sodium hydroxide. Molarity is essentially a conversion factor. Okay, so molarity is, for instance, you have 3.5 molar solution of hydrochloric acid. It means that 3.5 moles of hydrochloric acid is in 1 liter, or 1 liter of the solution contains 3.5 moles of hydrochloric acid. So this is a brief summary with examples of what molarity, mass volume, and mass percentages are. Now, often solutions have to be diluted. For instance, when you make orange juice from concentrate, you essentially dilute the solution. In dilution, the water is added to the existing solution and the volume of it increases. As volume increases, concentration decreases, but the amount, the mass of solute in the solution remains the same. So moles of the solute are the same. What changes during the dilutions are concentrations and volumes. So for percent concentration, you can write this equation that initially concentration by volume product is equivalent to concentration by volume product after the dilution. Same can be written for molarity. You just need to replace the concentration in percent by the concentration in moles. So let's take a look at one of the problems here. So you have 0.5 liter of 6 molar hydrochloric acid. You dilute it to 1 liter. So you can essentially write an expression here. Original molarity multiplied by original volume is equivalent to final molarity multiplied by final volume. From this equation, you can find that the molarity after the dilution can be expressed by this algebraic equation. M1, the original molarity, is 6 mole per liter. The original volume is 0.5 liter. The final volume is 1 liter. So by solving this little equation, you get the answer of 3 mole per liter hydrochloric acid. That's the concentration after the dilution. Now, in our next chapter, we're going to discuss the osmosis and dialysis, why it's important, the solution that is used to maintain the blood volume in patients, so-called isotonic or physiological solution, 0.9% sodium chloride. As we mentioned before, solutions are transparent. They don't separate, well, at least chemically, and they contain ions, molecules, very, very small particles. they can't be filtered through the filter, but they can pass through semi-permeable membranes. Like solutions, colloids have medium-sized particles. Colloids, just like solutions, cannot be filtered. However, colloids can be separated by semi-permeable membranes. So here's some examples of colloids: plasma, butter, liquid and solid. Now you can see substance dispersed and dispersing medium. For instance, mayonnaise, it's a liquid dispersed in liquid. Blood plasma, it's the solid dispersed in liquid. In case of dust or smoke, it's a solid dispersed in gas, and so on and so forth. Unlike true solutions and colloids, suspensions are very non-uniform mixtures. They're heterogeneous. The size of the particles is pretty large, and eventually suspensions will settle. The particles will settle out of the solution on the bottom of the vessel. Suspensions can be filtered, and in order to stay suspended, they must be stirred. Examples would include platelets from the blood, the water that is muddy, and various lotions. So this is the comparison of the solutions, colloids, and suspensions. We need to know the properties of these three. And this is the graphic comparison. So here you can see that circles represent solution, triangles, colloid, squares, suspension. Suspension settles on the bottom, can be filtered. And only true solution, the particles in the true solution, can cross so-called semi-permeable membrane, while colloids and suspensions will get stuck inside. That brings us to the conversation about osmosis. In osmosis, water, or solvent, flows from a lower to a higher concentration of a solute. So, level of the solution with the higher concentration of solute starts to rise, and eventually concentrations of two solutions become equal with time. So osmotic pressure is the pressure equal to the pressure that would prevent the flow of water into the more concentrated solution. Kind of how can you resist the osmosis itself? Osmotic pressure is becoming bigger as the number of dissolved particles in the solution increases. So this brings us to the process called reverse osmosis. When we apply pressure that is greater than the osmotic one, we apply this pressure to the solution, thus forcing the solution through the purification membrane. The flow of water in this case is reversed compared to osmosis, because water flows from the area of a lower water concentration to an area of higher water concentration and leaves behind the molecules and ions in the solution. You can use reverse osmosis to purify salinated water, to desalinate it, and obtain pure water from the sea. Some states in the Persian Gulf use reverse osmosis to obtain water that is precious, the desalinated water from the sea. However, this process requires an enormous amount of energy. Now, based on the concentrations of solutes, solutions can be divided into isotonic, hypertonic, and hypotonic. So isotonic solution is defined as the solution that exerts the same osmotic pressure as bodily fluids, such as the fluids in the red blood cells. So 5% mass volume glucose or 0.9% mass volume sodium chloride is isotonic solution. And since the concentrations, the osmotic pressure is the same, the red blood cells in isotonic solution do not change. They shape, they retain their normal volume. Hypertonic solution has a lower solute concentration than normal bodily fluids, and it means that water flows into the cell by osmosis. So cells swell, eventually burst, leading to a condition known as hemolysis. In hypertonic solution, the concentration of solutes is higher than the concentration within, for example, red blood cell. That results in shrinking, a crenation. Red blood cells decrease in size,
and basically water goes out of the cell, and the water is basically sucked out of the cell. Now in the process called dialysis, the solvents and the small solute particles pass through a membrane, through artificial membrane. The large particles stay inside, and small particles leave. So dialysis is used in the process known as hemodialysis to remove waste particles such as urea from blood.